And welcome everyone back to Beyond the Forecast. We are here, it's Monday, and we are now into what we call a free week here with the team. We don't have an underlying theme for this week. Next week will be Fire Weather Awareness Week. So essentially brush fire, grass fire, everything that goes along with fire season, fire danger. So we are going to be doing that next week. But this week, we're wide open. We will talk about a little bit of everything. And today's episode, we're going to start with precipitation. Meteorologist John Gross is going to break down all the different types of precipitation you can see. And let me tell you, it's right on time because we basically saw every form of precipitation this past weekend here in Michigan. And then we sit down with meteorologist Haley Fiaschetti, and she's going to break down weather balloons for you, what they are, what they do, and why they are so important for us and you here not only in northern Michigan, but across the United States. Trivia time. Now, if you recall back to Friday, I know it was a while ago and we've had a lot of things happen in between, but we asked you, what does a hydrometer do back on Friday? Does it measure humidity? Does it measure water? Does it forecast snow or predict floods? Well, this one's a little bit trickier. Maybe you don't always see a hydrometer or think of it, but it measures humidity. So there you go. Learn a little bit. Now, today's trivia question is, we want to know, where is the lightning capital of the world? Where do they get the most lightning? Is it India, Ireland, Venezuela, or Russia? Weigh in. That QR code down there, scan it with your phone, and it'll take you to the link where you can place your answer. Viewer photo of the day today, brought to you by Great Rooms, is sent in from Megan Hagedon, who said she was in her kitchen and caught this beautiful woodcock in her yard out the window. So that is a pretty cool picture, first off. And second, look how gorgeous that woodcock is. Thank you, Megan, so much for sending that in, and thank you to Great Rooms for sponsoring viewer photo of the day. But coming up next, we are going to be jumping into our show and talking about the different forms of precipitation. Meteorologist John Gross breaks down all the different types that you see and how they form. It's a little bit of science for you. And then after that, we're going to be jumping in with meteorologist Haley Fiaschetti to talk about weather balloons, exactly what they are, what they do, and why they're so important, and why they're getting cut back a little bit. We'll have those details coming up on Beyond the Forecast.
Hey there, everybody. Meteorologist John Gross, and today we're going to be talking about different types of precipitation, how they develop within the atmosphere, and the types of temperature, or at least the temperature profile that you need in the vertical to get different types of precipitation. Now, we've all experienced different types of precipitation depending on where you're located, where you lived, where you do live right now, maybe places you visited in previous trips before. Some of the most common ones that we talk about, rain and snow. But there are a few other ones that we still can see, but you need a very specific temperature profile or things specifically going on in the structure of the cloud base, in the cloud itself, or just at different levels of the atmosphere. That can include freezing rain, that can include sleet, that can include graupel, and that could even include hail. So let's go ahead and talk about it, and the ones that we do know and ones that maybe we're not as familiar with. So here's a look at it. Our 3D box, you're still talking about the atmosphere again, from the surface all the way to the base of the cloud. And at the base of the cloud, we're always talking about those temperatures near, if not well below freezing. So a lot of what we usually start with as far as precipitation goes is usually in the form of either an ice crystal or a snowflake. But depending on how our temperature profile is within the vertical itself, from the base of the cloud all the way down to the surface, that's when you can get those different types of precipitation. So let's go ahead and talk about, or at least start with one that we're a little bit more familiar with, rain. So usually when you're talking about rain, it's above 32 degrees. When we say above freezing, remember in Fahrenheit, that's above 32 degrees. In Celsius, that's above 0 degrees. But we're going to be talking about Fahrenheit here. So above 32 degrees all the way from when that droplets, or at least that snowflake, is moving throughout the atmosphere. It turns from that solid to a liquid, and then it falls as a raindrop all the way down to the surface. Things we already know, right? Let's go ahead and jump into one that we are maybe a little less familiar with, at least how it works. freezing rain. And you need a very specific temperature profile to obtain freezing rain. Now again, you start off with that snowflake base of the cloud, and then you have an area of the atmosphere where we're really talking about those temperatures near, if not just above freezing, so above 32 degrees. So you have it staying rain for most of its travels all the way down to the surface, but as you get to the surface itself, you're talking about temperatures near, if not just below freezing. So you could have temperatures near 29, 30, even 31 degrees, and that raindrop will literally freeze on contact or whatever it comes into contact with. So, for example, here that we have in this diagram, you can have icicles forming on trees. You can have icicles forming on power lines. You can have icicles forming on your car. Anything that raindrop can come into contact to. And that's when you can start to run into some major problems, especially if you're doing some traveling, icy roadways, bridges, overpasses. Those can become very, very slick very, very quickly. You also could talk about potentially if you have enough ice accretion. That's how we categorize ice accumulation. You can talk about power outages, and that also is not good news when you're talking about ice. So that's freezing rain. Let's go ahead and talk about sleet. And here's a look at that profile in 3D. Again, you start off with the snowflake, but our above freezing layer in 3D, remember in the atmosphere, it's a lot thinner. So you have just this little area now where the temperatures are near or above 32 degrees, but you've got a bigger freezing layer, at least temperatures below 32 degrees. Remember with freezing rain, it was very shallow, close to the surface. Now we have increased that area, or at least in 3D, as you're going up in the atmosphere below 32 degrees. So that raindrop, eventually it refreezes, and there's enough time for that raindrop to now freeze back into what we call an ice pellet. So you're not seeing that raindrop freezing on contact. Now you're seeing it form from that raindrop back to an ice pellet. So you can kind of see it. It's usually a little circular object, and you can kind of hear it tinging based off of what it comes into contact to. So a good example I like to think of is if you ever have a window nearby you, if you're inside and it is sleeting, you might hear a ting-ting on your window. That's a good indication you're talking about sleet and or ice pellets. Now, usually sleet, you're not talking about a lot of accumulation. It's hard to get a lot of accumulation when you're talking about sleet, but that's what you definitely are talking about, or at least that's what you're seeing when you do talk about those ice pellets occurring with a little bit less of that area in the atmosphere above 32 degrees. So that's sleet. And as we continue on, we all know what snow is, especially here in the state of Michigan. We've seen our fair share time and time again. Now, you can talk about different types of snow. You can get lake effect snow, which is primarily coming right off of the Great Lakes, or you can call it what we say is system snow. So usually that's gathering moisture from another source. That could be the Gulf, that could be another body of water, or just bringing in moisture from a different area, and that's what we're usually associating with an area of low pressure. So that's the differences between types of snow, or at least where we can get snow. But snow itself, again, the entire column from the base of the cloud all the way down to the surface below 32 degrees, so that ice crystal never has time to melt, and that's when we start to see the snowfall accumulations that we can see. And we know dear and well that snow can pile up to several inches, or even in some instances in the decades that we have observed these winter storms, several feet of snow. So that's the main four that we talk about. I also want to go ahead and talk about something you might not be as familiar with. We call it growlpool. Now, usually when we're talking about growlpool, these are usually occurring when we're talking about spring storms. So generally at the surface, during the springtime, you can talk about temperatures getting just above freezing. So you might be talking about some 40s. You might even be talking about some low 50s. That's usually common for the temperatures for us at the surface. So remember, here's a look at the cloud. And remember, as these clouds are going up, or at least when we have a very strong updraft within that cloud, that's what we can categorize it more as a cumulonimbus cloud. So as we continue to get these liquid cloud droplets within the updraft itself, moving into an area of the cloud that is below 32 degrees, that's when we do start to see those cloud droplets freezing. And as we continue on here, or what we call icing, those droplets again, they become what's called supercooled. So they drop well below 32 degrees, and then those supercooled liquid droplets, they start to freeze onto existing ice crystals. So this is a process that we call riming. And once we start to see that happening, it starts to become a little bit what we'll call crusty, or it kind of breaks down very, very easily. If you've ever held a piece of grapple in your hand, I kind of categorize it as Dippin' Dots. That's a good way to look at it. So as you're looking at that icing, again, supercooled water droplets, they start to collect on existing ice crystals. So you have that ice accumulation on there, what we call riming, and then the weight eventually increases. So kind of similar to the thought process of when we're talking about hail formation, but instead we're talking about grapple. Eventually that weight becomes too much, and then it falls down to the surface. I'm Meteorologist John Gross for Beyond the Forecast.
Thanks, John. Now, coming up next, meteorologist Haley Fiaschetti sits down and tells us what a weather balloon is, what they do, and why they're so important to you and I. We'll have more on that right after the break.
Welcome back to Beyond the Forecast. It's meteorologist Haley Fiaschetti, and today I'm sitting down and talking to you guys about weather balloons. You might have heard that term the past couple of weeks online or on the news, so I decided it's best to just sit down with you guys and have a conversation of what weather balloons are, how we use them, and why they help our forecast in northern Michigan. So let's get into it. First of all, what is a weather balloon? Now, a weather balloon is the best platform for us to get observing temperatures, winds, relative humidity, pressure, really anything you can get as a current. That's where we're going to use a weather balloon for. They've actually been around for quite some time. Mainly, the National Weather Service is in charge of launching a weather balloon twice a day, 8 o'clock in the morning and 8 o'clock at night. This has been going on since the 1930s, so pretty early in American history for weather. We've been using these weather balloons to help us get a current look of what the weather looks like all across America. But what's actually interesting is weather balloons in some sort of way have actually been seen in history since the 18th century in Europe. People actually using kites or umbrellas, hooking up a thermometer to the machine and trying to lift it up in the air to get a current temperature at a higher atmosphere. We've been seeing this in early weather history for quite some time. So to be still using a product like this and to be practicing weather launches today shows just how important this really is to what we do every single day. Now you might be wondering, how do we actually launch a weather balloon? It's actually a really cool process, and if you can, go to your local National Weather Service to see it. It is something to watch for. In college, I got the opportunity to sit on a few weather balloon launches, even in high school. What you first do is you start off with a latex balloon, and they fill it up with helium. Normally, there's an observer from the National Weather Service who is in charge of this, the first one being at 8 o'clock in the morning, and they fill up the balloon with helium, attach a bright orange parachute to it, also a string with a radio sound on it. Now, a radio sound is a sensor that keeps track of the temperatures, the pressure, the relative humidity, and the winds. Kind of your machine that holds all the data. It's really tiny. Honestly, it's kind of like this size, very light, very tiny. It's able to lift up with the balloon and the helium to get all that information. When the observer starts, they normally turn on the radio sound first to get your baseline. Now, the baseline is kind of what we call your constant. So at the surface, at the ground level, you're picking up what the temperature is, what the pressure is, what the relative humidity is, the winds, what we all know at the ground level. So when you can start the balloon, you'll see the difference from what's happening at the ground and what's happening all the way up in the atmosphere. The observer then lets go of the balloon, and the balloon rises up with the radio sound, with the parachute, and gets all the information as it continues to go up in the atmosphere. And that's where we can see that difference in pressure, in winds, and in temperature. All really important information that us meteorologists use to determine whether a storm is coming in or if we're going to have quiet, calm, sunny days. This normally happens twice a day. In the morning to get your morning sound where you can pick up the information throughout the day, and then also at night. As it's rising in the atmosphere, we back on the ground level, the National Weather Service is getting information every single second to see the difference of what temperature is happening as you rise in pressure in the area. Now, for us, our local National Weather Service, Gaylord, they get to do it and they'll tell us what they see via sounding. So once the balloon pops, the parachute and the radio sound fall back to the ground level, and we can pick up the information from that radio sound on the computer. That then produces a sounding where we get all the information and kind of a data pinpoint of what's going on in the atmosphere. And that helps us in many different ways. That can help us with our local forecast. If we see severe weather, we'll see a change in pressure or in winds, and that will help us know how a system's going to affect us. It also helps with computer modeling. Every single day when we forecast, we use models on the computer to help us see into the future. And with that, soundings from our weather balloons help us determine what the future is going to look like and kind of give us a little bit more of an insight of what's to come, especially when it's all across America at the same exact time. So if a weather sounding looks crazy to the west of us, we can then be prepared to see what's going to happen to us in the future. You'll even notice that during severe weather, we might actually get more than 2 soundings a day. Depending on the severity of the weather, we sometimes will issue more than 1 so we can actually see in real time what's going on in the atmosphere. This helps us with local forecasts on air when we deliver the weather to you guys, but also in research when meteorologists and researchers across America or in college, they can help see how these weather soundings help in the future when it comes to the weather. So that's kind of breaking down how important these weather balloons are to us and how we use them every single day. Now, weather balloons are really important here in northern Michigan, especially because of how dynamic our weather actually is. We see different things happen all the time. I mean, take the past couple weeks, for example, seeing winter temperatures and then record-breaking temperatures, feeling like the summer almost for a few of us. Those weather soundings gave us an insight of what we could expect across northern Michigan. And unfortunately, we are actually seeing a decrease in weather balloons moving forward. Gaylord, who normally produces about a weather balloon twice a day, just got downgraded to only doing it once a day in the morning. So that means we're actually in the dark at nighttime for what current situations are happening in the atmosphere, which can really hinder our forecasts moving forward, especially during a severe weather outbreak. So that's why weather balloons are super, super important to know what's actually going on in the atmosphere. Even in Green Bay, they're losing a weather balloon sounding a day. And that also helps us as they see what's happening over the lakes. And that's going to impact us as we head into the summer months as well. So that's just a little insight of how important weather balloons are, and some of the cuts that we are seeing for weather balloons are impacting us on our everyday forecasts. But we'll have more information and deeper information on those weather balloons coming up.
Thanks, Haley. Always great to look back at what works with weather and what continues to work really well for us. Now, coming up, we deep dive again into our live streaming podcast that we filmed last week about severe weather. We'll have more on that right after the break. And welcome back, everyone, to Beyond the Forecast. And thank you for hanging out with us. We truly do appreciate it. For Meteorologist John Gross, Meteorologist Haley Fiaschetti, I'm Chief Meteorologist Michael Stevens, and we'll catch you back here tomorrow for more Beyond the Forecast. Take care, everybody.